When a bunch of electrons congregate in one place, their combined charges build up to a certain level of electric potential energy in that object. For example, when I rub this rubber balloon on my wool scarf, it causes a bunch of the electrons from the scarf to jump over on the balloon. Now the balloon is negatively charged because it has a surplus of negatively charged electrons, and the scarf is positively charged because it has a shortage of electrons. This imbalance of charge means there's a difference in the electric potential energy between these two objects. And that difference produces a force which tries to move the excess electrons from the balloon back towards the scarf to equalize the charge. We use the term voltage to describe the difference in electric potential energy between 2 points. And we'll use that imbalance of energy to push electrons around when we create electric circuits. Voltage is measured using a unit called volts to describe how much more or less potential energy there is in one place compared to another. When describing the voltage of something, it's critical to know what the point of reference is. What are the volts relative to? That point of reference may not be explicitly defined when working with common voltage sources, but you're still expected to understand what that voltage means. For example, in a 9-volt battery, that single number, 9 volts, means there's a 9-volt difference in potential energy between these two terminals. There's an insulative barrier inside of the battery that separates the two halves, and the battery works using chemicals inside that act like a pump to move electrons from the positive side to the negative side. It moves just enough electrons to maintain that 9-volt difference between the positive and negative terminals. Looking at another power source, the electrical outlets in North America operate at 120 volts. That voltage is describing the potential difference between these two terminals. By convention, the terminal on the left is called the neutral line and acts as the point of reference, and the hot terminal on the right is 120 volts relative to the neutral terminal. In a complex electrical system with lots of components, different points throughout the system will likely be operating at different electric potential energy levels. Therefore, to keep track of the voltages at each of these points throughout a system, it helps to have a single point of reference. The term ground or common designates that single reference point, which is used to describe the voltage at other points throughout an electric circuit. The term ground comes from the fact that many large electrical systems, like the wiring in your house, are connected to the earth and literally use the ground as that single point of reference. In practice, the terms common and ground tend to get thrown around and used interchangeably, so it's important to always understand what the voltages in a circuit are actually referenced to. To illustrate how multiple voltages can be referenced to a single point, I'm going to use an analogy relating electricity to water. In this analogy, you can think of a voltage like a difference in pressure. This cooler represents my electric system, and in it I have 2 cans of carbonated soda. I've chosen this can to act as my common point of reference for the system, so I've labeled it with the symbol for electrical ground. This other can, labeled A, represents some other point within the system. Right now, both cans are at the same pressure, which represents their electric potential energy. Since there's no difference in potential energy between these 2 cans, can A is at 0 volts relative to the reference can. If I shake up can A, that'll increase its internal pressure, which means can A will have a higher potential energy than the reference. Now can A represents a point in my system with a positive voltage. These cans are both in sealed containers, so there's nowhere for the soda inside to go, but if I was able to connect them together with a straw, soda would flow from the high pressure in can A towards the lower pressure in the reference can. And there's another can of soda in my cooler, and it's conveniently labeled B. Can B was opened a while ago, so the carbonation in it has escaped and it's gone flat. Since the pressure in can B is lower than the reference can B represents a negative voltage in the system. For this analogy, I shook and opened soda cans to change their potential energy, but in an electrical circuit, we use components called voltage sources, like batteries and power supplies, which maintain a constant potential difference between 2 points. I can compare the voltage between these 2 battery terminals in the same way I compare the pressure difference between soda cans. I've connected the negative terminal of the 9-volt battery on the right to the positive terminal of the battery on the left. And I'm using that point as the ground reference for the system. Traditionally, black colored wires are used to connect the negative output of a power source, and red wires are used to connect the positive output. Point A is represented by the positive terminal of the right battery, so it's at positive 9 volts relative to the ground. Point B is represented by the negative terminal of the left battery, so the voltage there is negative 9 volts relative to the ground. The fact that point A represents positive voltage and point B represents negative voltage is dependent on the can I chose to serve as my reference for ground. If I had selected the open can to be my point of reference, which has the lowest potential energy of the 3 cans, then both of the other cans would have a positive voltage relative to it. This is that same circuit diagram as before, except I've changed which point I decided to call the ground reference to be the negative terminal of the left battery instead of the point in the middle. Now the point in the middle is at positive 9 volts, and point A on the far right is even higher at positive 18 volts relative to ground. We encounter a wide range of voltages in day-to-day life, ranging from the relatively small signals that come from an audio jack of an MP3 player, which are usually less than 1 volt, all the way up to the high voltage transmission lines that carry power over long distances, which operate at over 115,000 volts.